Good evening, everyone. We will wait for 5 minutes and then we will start. Good evening, everyone. So, my name is Abhishek Munshi. I am a PMRF research scholar at IIT Jodhpur. So, I will be the teaching assistant for this class. And this is the week 5. And this week we will discuss about the heatsink design and thermal modeling. I hope you all understand the previous lectures. So, regarding the heatsink design and thermal modeling, we will discuss this week. And after discussion, we will solve some problem related to it. Okay. So, basically, if you design any kind of converter, you will see that there will be some kind of cooling system. Right. So, what happens? There will be some kind of cooling system, like whether it will be natural, forced, liquid. Mm. So these are the. This is a heat sink. If you see over here, and it is cooled by means of a fan. In case of an inverter, you will see this kind of heat sink, and also there is a fan to heat bypass the heat over there. And this kind of copper cooling system are there in latest mobiles. You see this kind of cooling heat system also. Okay. So so basically what we do in thermal modeling in heatsink design to determine the component temperature and in terms of the thermal resistance, thermal capacitance, thermal time constant. So basically what is that? So if we see that what is thermal resistance, that is basically the uh, difference between the temperature of the material. If you see that any power device will absorb some kind of heat, there will be an ambient temperature. If you see from the image, you can see that there this is the device, right? There are a lot of heat sinks are here. These are the examples of some kind of heat sinks, the shapes for various MOSFETs and IGBTs. This is a PCB 3D model where you can see that for this MOSFET, a heatsink has been used. So practically the heatsink should look like that, right? In some cases, they also use heatsink behind of this PCB. Uh, Behind of this PCB also they use if the heating element is more. Okay. So what happens in case of the heat sink whenever you're using a heat sink? Suppose this is your MOSFET, right? So in the MOSFET, we use some kind of thermal compound, grease type material, and after which we use the heat sink. Okay. So here you can see that there is this is the heat sink. This is the MOSFET. So it should have a junction temperature, junction to case temperature, case to ambient temperature, heat sink to ambient temperature, right? Case to sink temperature. Okay, so there are a lot of temperatures and resistances we should have to consider while designing a heat sink for a specific MOSFET. So if you see this is the heat sink, right? So this is the heat sink, and this is our MOSFET, and there is a case. You can consider that this is the case of the MOSFET, after which there is a junction point where the MOSFET touch the heat sink, right? So there will be different resistances according to that. So this is my junction and this is my ambient. Ambient means that is the surrounding air temperature. Okay, and this is the temperature of the case. This is the temperature of the sink. Okay, so in between the junction to case, there is a resistance R theta JC. Case to sink, there is a resistance R theta CS, and sink to ambient, there is a resistance R theta SA. So there are three resistances according to this, that from junction to case, in between of that there is the junction to case resistance, then the sink temperature, in between of this temperature difference there will be case to sink, and this is ambient or atmospheric normal temperature, in between of which this is RSA. So if you have to consider the total resistance, that will be RJC plus RCS plus RS. Fine. So that is how you can able to calculate how much heat can be dissipated. Okay. So what is basically thermal resistance? So thermal resistance, from here if you see that it is the function of the thermal power. So basically the temperature difference between 2 points is the thermal resistance and power component. Okay. So how could you write these things? So from the expression you see that thermal resistance is degree Celsius per watt. That means the change in the temperature by power can be written as thermal resistance. So if you have to consider how much power lost, then that will be the temperature difference by the thermal resistance. So if we don't use any heat sink, then that temperature is called, that is the junction to ambient temperature, because in that case if you are using a directly a switch that is exposed to the atmosphere surrounding, so we have the surrounding temperature, that is the ambient, and we have this junction temperature. So how much heat it will dissipate, that is the R theta J, that is equal to theta J minus theta A by P. So how much power it will dissipate, theta J minus theta A by RJA. So by mean of this formula, we can able to solve the basic heat dissipations in a switch. Okay. So in your data sheet, you will find these values. Now, if we consider the heat sink, now if we consider the heat sink, then we have junction, after which we have the case, after which we have the heat sink, and then ambient. So in that case, what will happen? We have the power dissipation, the total change in the temperature with respect to the junction to the ambient, and we have to consider all the three resistances: the junction to case, case to sink, and sink to ambient. All the three resistances, thermal resistances. Okay. So this is what the heat sink power dissipation. Fine. So after this, if you have any doubts, you can ask me or note it down in your copy. I'm giving 5 minutes to understand this, and after which I will continue. Jaya Kumar, kindly mute yourself. So I hope you all understand the basic of the heatsink design. So as I said that whenever there is if you see that the temperature, the junction temperature with respect to the our loss, the total average power loss across temperature, it will look like this. So basically what happens, it will start from your ambient temperature and it will move on like this. So if it increase from the uh, uh, temperature you set behind that, then it will goes off. So what is the average power then? That is the junction temperature minus the ambient temperature divided by all the three resistances as I said. So if I have to calculate the sink to ambient resistance, then how could you calculate it? Then basically you just divide it the change in temperature by the PD average minus these two resistances. Right, so that is what the sink to ambient resistance you got. Okay. And based on which you can say that this is at if you simulate it in the LT spice or anywhere and you got this PD average for any MOSFET, for example, uh, any MOSFET if you select like this, and if you took this junction temperature based power from there and put it here in a current source, and you put these resistances that is given in a data sheet of any MOSFET. If you go through any data sheet of MOSFET, you will find that these resistances are given. You have if you have to model it like this. If you put this resistances value and if you know this power dissipation and change it into current source, then you could see that after simulation, if you check this point, the junction temperature, you can see that how much temperature it will rise or not. You can able to check it. But every time you start, you can see that this will start from the temperature of ambient. Okay, because the circuit is not ground with respect to the temperature ambient, right? So that is how you can model the temperature of any MOSFET, any switch device in mm, spice like simulations and by knowing the datasheet's value of these three. Okay, and is it clear to everyone how could you model these things? And if you gone through any kind of a proper datasheet of any manufacturer datasheet from like Nexperia, you will see that the data sheet there will be some kind of values given over there other than these thermal temperatures. There are some kind of thermal capacitance also, so we can able to model it in a different way. That is called thermal modeling. But after this, if it is not clear, then you can ask me. So kindly note it down in your copy and try to understand that how could you able to model the temperature of any device in case of, right? So this is how the temperature is not fixed. It will rise and down like this. This is the junction temperature. So if junction temperature will reach after a certain limit which you set, for example, for a PCB design 120 degrees Celsius to 125 or 150 degrees Celsius may be considered as the normal temperature. So if that exceeds that junction temperature exceeds then 130 to 150 temperature, then if we use some kind of NTCs and all to consider the temperature protection of that converter. Okay. So is it clear? So if it's not, then try to note it down in your copy and ask me if you have any question regarding this. feel free to ask about it, because if you know these things, these are the advanced things, and if you're able to, you can able to model it in spice also to understand the junction temperature of any MOSFET or anything before going into the actual circuit while designing. Okay, so try to note it down and also ask if you have any doubt. I hope you all understand and note it down in your copy. So, as I said that while doing a thermal model, uh, if you go through the datasheet of any MOSFET in Nexperia, that will be more helpful. If you go through the datasheet of any MOSFET in Nexperia, you can see that other than this thermal temperatures resistance, they will give some kind of capacitance value also. So basically, this is the RC modeling of thermal modeling. This is the most conventional method of modeling the thermal for any kind of switches. Other than that, you can also model in case of any finite element analysis software like ANSYS, Flowthumb. You can do that in also in those softwares where you can, if after designing the PCB of your converter, you can put it over there, and if you mention those values, then they will give the temperature of those mm, areas where the temperature will be high or the temperature will be low. That will be the FE analysis. Okay, the thermal analysis of why doing ANSYS and all. And another best way of doing understand how much heat is there is in the real life situation when you're uh, trying to use the converter, you can use any thermal image camera. By clicking the photo of the thermal image camera, you can able to see that how much heat has been in the converter at which areas. Okay, but the most easiest and the most understandable method mathematically if you do the thermal modeling, that is basically the thermal modeling method by using RC thermal model. Okay, so RC thermal model can be of two type. One is core type, core network, another is Foster network. So if you consider the core network, you can see that you have to uh, put the capacitors and resistance in this manner. Okay. And in case of the faster network, you are adding the RC network like this. So after making this circuit, if you check the temperature, junction temperature, and this one is with respect to the ambient temperature. Okay. So if you check the thermal temperature at this node, you will be able to see how much temperature rise your converter should have. Should be like that. Okay. So it will start from the ambient temperature. If you start from 25 degree, it will rise up to the rising temperature. For example, if your converter is heating up to 50 degrees Celsius, then if you start from 25 degree as the ambient, then it will heat up to 75 to 80 degree. If you start from the 80 degree as the ambient temperature, then it will heat up to 130 to 135 degrees Celsius, and accordingly you have to put the base temperature up to which you can the converter can able to sustain it. Okay. So if you gone through any data sheet of an Xperia of MOSFET, you will see that they will put these values, this R value, C values, and you can able to model it in spice and able to see how much heat it can be considered. Okay. So if you have any doubt, you can ask. So this is the way of understanding how much heat you can your converter switch can sustain. Okay. So before moving into the actual circuit, you should have to understand these things. Okay. So note it down, and if you have any doubt, you can ask me. So this is also called pulse power dissipation. Okay. So try to note it, and I'm saying one thing more. How could you model it in the spice, right? So to model it in the spice, to add a slide. If you gone through the data sheet of any MOSFET like BUK, any series of Nexperia, you will find that they will give some spice thermal properties. Suppose they will give some C1, C2, dot 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 up to suppose C7. Also the resistances. So first of all, what we have to do, you have to take the model of the MOSFET. To take the model of the MOSFET and to apply a VD, and you have to give a gate pulse like this. So if you give a gate pulse over there for a duration of time, that is, since this is pulse dissipation method, so obviously by means of the spice you can able to understand how much heat it dissipated. Okay, that is basically the power. If you use LT spice, then by means of alt shift you can able to if you click it here you can able to understand how much power dissipated here. So knowing that value, suppose it is x into I plus y into v like this, you just have to put this as a behavioral current source and put the value this one, And after which you have to model it in either core method, either in Foster method. Foster method is more preferable. So you can able to model that. This C1, this is R1. Then you have to put this value like C2. Sorry, this is R2, C2, R1, C1. Okay, like this, dot, dot, dot. And finally, after the final one, you have to put as a voltage source, you have to put the temperature or ambient. Okay, either it is 50 degrees Celsius, 25 degrees Celsius, 80 degrees Celsius, you can put it over there. And then you have to run the simulation and you have to check the temperature at this point. That will be the junction temperature. Okay, so that is how you are able to uh, model the thermal model of any MOSFET. So this is the process of doing thermal modeling of any MOSFET. But before, okay, another method of doing it in SPICE is that if you see that if you consider any MOSFET model, you will see in case of some MOSFET model, they in the SPICE they already given the temperature parameters included in it. The temperature parameters have been included in it. In that case, you don't have to do this thermal modeling in Core or Foster method. You can directly simulate the MOSFET and you can check the junction temperature directly without going into these RC methods. So if you have the thermal model included in your SPICE of the MOSFET. If you don't have, then you have to go through by these methods, just core network method or Foster network method. Okay. So here also you can see that this is the pulse which we give in the MOSFET region, and after at that region we are able to see that how much temperature it will rise at that period of time and not. Okay. So that is what the thermal modeling of any kind of MOSFET switches. Okay. So now you can note it down and note down the process, and after which we'll move into next thing. Fine. So this is how the thermal models can be done. What is basically the Foster model, which is more preferable. And the Foster model is derived by semi-empirically fitting a curve to the threshold ZTH, the result of which is a one-dimensional RC network. You can see it from here. So this is the Foster network. It's one, two, like this. Let's go on up to n number of RC by which you can able to model those. This RC curve in a Foster model do not corresponding to any geometrical location of the physical device. These values cannot be calculated from the device material constant, but it should have to be given in the datasheet by the manufacturer, or they should have to keep the model of the thermal. Otherwise, you don't able to solve it. As you don't able to calculate this RC inside of a MOSFET or any switch, right? So finally, I knowing the RC model cannot be divided or interconnected through. They have a RC network of a heat sink connected into it. Okay. By knowing the TJ, T theta inside of the datasheet, they already modeled it into it. So I have to put those things. So faster RC model have the benefit of ease of expression than thermal impedance ZTH. As I said that this is a semi-empirically fitting the curve of the thermal impedance. The faster model can be done. So by measuring the heating or cooling curve generated by this Z curve, you will able to fit it. So in the data sheet, you will able to see that there is a curve that is called Z curve that is given over there for different temperatures, right? So the formula for calculating it is ZTH summation of 1 to n Ri1 minus x1 into 1 minus t1. So this model parameter RICI, which you consider are thermal resistances and capacitance, which are used to build this thermal model that is shown over here. This R1, R2, that dot dot dot. Okay. The next is for Foster model. You already seen it. The core model is also considered of RC network like this. The CRCR, the branch way. Here the thermal capacitance are well connected to the ground. Ground in the sense is ground that is basically the thermal temperature ambient. This is not ground as zero. This is the ambient temperature which we consider as the ground. Okay, so this is how we are able to model the core model. Okay, the nodes in the core model can have physical meaning, allow access to temperature. You can able to check the temperature at this node. Similarly, in Fosters, you can also able to check the things at this node like this. In Foster, if you are using like this, you can able to check the temperature at these junctions also, but this will be the junction temperature actual. Okay, so that is how you can able to model any MOSFET or anything else. But uh, you can also, yeah, while designing the PCB of any converter, you should have to consider the RC thermal model for the PCB also. You should have to know the capacitance of the PCB by you should have to calculate it by knowing the copper, how much copper it uses. By knowing that thermal temperature, you can able to calculate the PCB's RC models and you can put over there. By knowing the material, mostly it's FR4 materials are used, right? So for FR4 there is a specific values you have to put it that, and you have to model the PCB's RC also, and in this way you can able to completely thermal model a converter. Okay. So as I said, the pulse dissipation method, there you can see that this is there in the datasheet. There will be a Z curve. As I said, the thermal response with respect to the rectangular dissipation. So I said that there will be some curve, and according to which they put the values of the R and C various junctions. So you have to put those values while modeling. Instead of that, you don't be able to understand this. So in some cases, in some data sheet, they didn't give the extensive value of all the R, C, RC. Rather, they give this thermal impedance as a whole, and you have can able to put that thermal impedance over here and can able to also calculate the rising temperature of this junction, how much temperature it can able to hold and how much temperature it will rise. Okay, so that is how we can able to thermal model any converter switches, converter totally with PCB, and have a predetermined value of the temperature rise of the converter. So now how to select the heat sink. If you see that how to select heat sink. So while selecting the heat sink, you should have to know these temperatures. These were given in the data sheet. If we go through any MOSFET data sheet, you will be able to see that they give this junction temperature, case temperature, and all, and based on which you have to calculate the resistance. And based on this resistance, you have to choose the heat sink from the market. You have to choose the heat sink which has a adequate value with respect to this theta RSA so that it can withstand that amount of temperature in between of this. Basically, this is the sink to ambient temperature. So whenever you're using a heat sink in between of the after this MOSFET or switch to the ambient, they should provide a thermal insulation to the um, switch so that it doesn't have heated so much heat and it will not affect to the other component of the converter, right? So proper designing of the heatsink is important. I see that many people design PCBs without knowing the proper values of their heatsink. They just put a heatsink but buying it from the market. Often it works, but doesn't that it will work every time. If you have a temperature greater than of that, then that heatsink will not provide any kind of insulations to your PCB or your converter. Okay, so there are a lot of heat sinks are available and they have a specific package base. Suppose for TO252, TO212. So these are the standard packages for through hole. For SMD, basically for SMD devices, we basically doesn't use any kind of heat sink mostly. In case of the SMD device, what we do is, I'm saying you the trick. So in case of the SMD device, suppose there is a PCB and you place your MOSFET, SMD MOSFET over here, right? So in that case, you can also use a heatsink above of it, but mostly in good practice, what happens? People use what this if this is your PCB, they use thermal vias around this. They use thermal vias, and since the PCB is made with copper, like F4 material, so what happens? It will help to dissipate the heat from this side to that side, and that is how, in case of the SMD devices, means surface mount device. In case of surface mount device, this is how uh, the designer mostly bypass the heat sink because it will create additional weight, and by means of these thermal vias, they can create heat sink easily. But in through hole, there is no chance because in case of through hole, the device should slant it like this from this side to that side. So in that case, heat sink is important. Okay. In SMD also heatsink is important, but you can bypass it by means of these tricks like thermal wires, thermal insulating resistance and all. There are some thermal jumpers are also available in market that's looking like resistances SMD, but basically they are thermal jumpers. What happens? Suppose if you are using a MOSFET SMD device here, but you have a component back of it and you don't able to do the thermal wires here. So if you don't able to create thermal wires because you have a component at the back of it, maybe just like suppose the gate driver is in the back side of your MOSFET, so that's in that case you're not able to do thermal vias to connect it. So on that case, you can able to create a thermal via here, and you can just connect it by means of this thermal jumpers. Okay. So these are the techniques we basically use in converter design heatsink for SMD component. But in through component, you can have to directly put the heatsink. So proper heatsink calculation is very important while uh, designing a converter, and you should have to keep it in your mind. Otherwise, if you put a random heatsink, then maybe it will happen that it will work, but maybe not. So you should have to go through these things and should have a predetermined knowledge about how much heat it can withstand your system. So for that, thermal modeling and heat sink is one of the most important part of design. Okay. So we will move into some problem solving, and before that, if you have any doubt, you can ask me because these are very practical things, and you should understand these things by your experience of designing converters. By knowing the formulas and by knowing this how to design, you can design it. But more and more, if you are able to design it by your own, by experience, you can able to understand these things. Like I said, for SMD devices, we don't often don't use any heat sink. We use thermal vias to connect it. We use thermal jumpers to connect the heat sinks with the. So these are from the experience of designing converters day by day. You can able to understand these things. So if you have any doubt, you can ask me because these are the most practical topics you should have to go through. Uh, Only solving the problem it will not help you in designing the converter in practical situation. Okay. So if you have any doubt, you can ask. Otherwise, gone through this before moving into the formula based problem solving. Okay. Fine, so I understand you already. If you don't have any questions, so moving into the problem section. So this is the problem. You should have to download the datasheet for IRA 530 NPVF, and I will give the datasheet over here also. So for designing a converter having a switching frequency of 100 kilohertz, its ambient temperature is given 60 degrees Celsius. The output voltage is 20, input voltage is 40. So that means it is a buck converter. And if you have to design the converter, while designing, you should have to go through the data sheet. So data sheet of this MOSFET via 530N, you have to calculate what will be the on-state resistance. Okay. Firstly, you download it. Or if you don't download it, you can able to see this here. Oh. So if you download it, you'll be able to see and top of it will be written. So what will be the value? Kindly download it and then say me the answer. So what will be the value? Kindly check it. Try to answer it in your comment box. So it is given here, right? So what will be the value? So RDS on is 90 milliohm, right? So this one is the RDS on 90 milliohm. If you don't even download it, you can able to answer it by seeing it here, right? Okay. Next question, you have to calculate the typical turn on time. Typical turn on time for which the data sheet is given here. I attached it. Try to calculate the typical turn on time. Given 2 minutes. Okay.
31.
I already had discussed this in before previous classes. So what will be the turn on time? So basically turn on time, that is this turn on time of any MOSFET should take the turn on delay plus the rise time. So here it is 9.2 nanosecond plus 22 nanosecond. So it will be 31.2 nanosecond. Okay. Next question, you have to calculate the turn off time for which same data sheet. So calculate the turn off time. Everyone was correct for the last question. Try to calculate this one also. So this is basically the on turn off delay plus fall time. So it is given 35 and 25. It is 60 nanosecond. So those who give the answer is correct. Maximum operating junction temperature. So maximum operating junction temperature is basically the TJ, the junction temperature. So it is also given in the data sheet. So what will be the value? Yes, it is absolutely correct. 175 degrees Celsius is given in the data sheet. That is the maximum temperature. So you are asked to have the maximum operating tension temperature. So maximum TJ is 175 degrees Celsius. If you are asked to have the minimum, then that will be minus 55 degrees Celsius. Okay. The next question, what will be the junction to case resistance? So here it is given. What will be the value? So here it is given. So it is 2.15 degrees Celsius per watt. Okay. Next question, what will be the sink case to sink resistance? That is R theta CS. So it is 0.50 degrees Celsius. So next question, before moving into that, I ask something. So we have this r theta cs. It's given as 0.50, right? We have r theta jc as 2.15 degrees Celsius per watt, right? We have tj 175 degrees Celsius, right? Now we have r theta ja also is given as 62 degrees Celsius per watt, right? So if we have an ambient temperature of around suppose uh, 60 degree, then can you say that what will be the power dissipation for this MOSFET? We have all these values in the datasheet, right? And we know the ambient temperature, that is you can able to select it because that will be the temperature at which you are conducting your experiment. So what will be the dissipating power? Can anyone calculate it? I'm giving 2 to 3 minutes. Calculate and say me what will be the answer. Someone answered it 1.78 watts. So how you solve it? Can you explain that in the comment section if you're not able to say it in the loud? Two of you have answered, right? So how you calculate it? Have you calculated it like this? The PD is Tj minus Ta by the sum of all the three resistances. 175 minus 60 by 2.15 plus 60. So if you solve it, it will be like that. Exactly. So that is how can able to calculate the power dissipation, you can able to select the heat sink also. Okay, fine. So we are moving to the next question. So here in this question, yeah, in this question, you're asked to have calculate all the losses: conduction loss, switching loss, and total power loss. Calculate one by one. I'm giving 5 minutes, after which we will solve it. Okay. So basically, we tried to give you knowledge how to design the its converter switches, uh, heat sink. Last class I designed about the snubber. So basically, step by step, you will to understand, right? Fine. So try to solve this one. Okay. So how we will calculate the pass loss? That is basically we have these values V in, V out, IL, RDS. So this is basically IL square RDS on into D. So it will be 2.88 watt. And what will be the MOSFET switching loss? If you know this, that is V in ISW into T1 plus T of FSW by 2. On the first or second class, I had derived all these conduction loss and switching losses formulas, so you can follow through that lecture. So it is 0.73 watts. So the total loss will be the sum of these two, that is 3.61 watt. Okay. So next question for your asked, what will be the sink to paint resistance? So try to solve it first, then I will show you the solution. Given 2 minutes to solve it. Okay, 2-3 minutes. So how we will solve it? So basically, what happens? So we have these values, right? Tj, this r theta has already calculated the p loss. So from where we can able to calculate it? So it will be 29.21 degrees Celsius per watt. Okay. So next question, select the appropriate heat sink for the design. So you should have to go through the data sheet of this heat sink, or otherwise you can able to see it the temperature rating, and you can able to say what will be the value, which one will be the best suited heat sink for it. So try to answer it. So what will be the value? So if you calculate it, then it will be 18.7 degree per watt. So that will be the best suited as you calculate it. Before is 21. So that's why. So now let's say heat sink. You have a fan of a 200 LPM is used at LPM. So R theta, calculate the rise in temperature. You have a heat sink value of 16 degree per watt. So try to solve it. So basically what to do here. So by the same formula, Tj is R theta J PD is plus Ta. So it will be 127.33 watt, right? So next, how is the performance of heat sinks enhanced? So try to answer it. We have 2-3 question left, and after which we will end this class. What will be the answer? It makes the heat sink more capable of dissipating heat. Okay. So next question: what is the primary factor that affects heat sink effectiveness? So what will be the answer? So it will be the thermal conductivity and surface area. Okay. Next question: which factors are essential for the heat sink size? So can anyone answer it? So I think all except this one, the kind of electrical connection, all are correct, right? So this is all for the regarding heatsink design and thermal modeling. So if you have any doubt, you can ask. I'm giving. Otherwise, you can leave. You can end the class here. So if you have any doubt, you can ask me regarding heatsink design. Otherwise, thank you very much. We'll meet in the next week with a new topic. Okay. If you don't have any doubt, you can leave. See, I had discussed it in previous one of the lecture, first or second, I don't know, remember it, but I discussed how to calculate it by I derived the formulas. Today I put the formulas directly. That's why. Uh, uh, so if you remember, if you go through that lecture, you can able to see that I already had derived it. So by derivation, I just put the formulas over there. Conduction loss and most probably in the first lecture I going to calculate all the values for the losses. I just put those values here today. You've gone through that. If you have any doubt, you can ask me. Anything else? Okay, fine. Thank you. Good night. We'll meet with a new topic at the next week. Okay.
Thank you.